We are looking at our notes packet. We're looking at section 5.1, part 3. We're going to be talking about how can we find derivatives with natural logs. Okay, so natural logs, that's when we have that ln. So first we have to know what the formula is. The formula is this. The derivative with respect to x of natural log x is always going to be 1 over x. There, in the back of the book, if you check an answer to a derivative, it might say x greater than 0. All that means is that this value of x has to be greater than 0 for this reason. If I have the natural log of x, the base is e, so e to any power would end up being a positive answer. So that's all this is saying, is that x should always be a positive value. And that's totally fine. We don't have to worry with that. The derivative with respect to x of ln of u. Well, this is for the case when we have something besides just an x here. If we have something other than the x, the derivative is going to be 1 over whatever that value is times the derivative of that value with respect to x. Another way to think of it is u prime divided by u. U prime is the derivative of u. U's right there. Okay? So this is just basically the chain rule with derivatives for natural logs. Look at the first problem. This would be our u. So the derivative of natural log of u, look at the formula. The derivative of natural log of u is 1 over u times the derivative of u. So what's the derivative of 3x? 3. And now we just simplify that, and that would just be 3 over 3x is 1 over x. That would be that derivative. For number 2, here's our u. So finding that derivative, y prime is going to be 1 over u times what? 2x, right? And then just combine those. So it's 2x over x squared plus 1. That's going to be our derivative. Okay, let's look at some more difficult ones now. All right, what about on this one? Well, on this one, we can see that this is a product, right? It's a product of variables. When we have a product of variables, we have to remember that if we want to take the derivative with respect to x of f times g, remember that product rule? It's f prime g plus f g prime. Okay, that was the product rule that we used to use. We haven't used it in a while though. So this would be my f, and this would be my g. So what's f prime? 1 times g, ln of x, plus f, which is x, times what's g prime? What's the derivative of ln of x? 1 over x. Good. So here's our plus. So we have to combine these two because they're terms, and these two. So when I multiply this, I get natural log of x plus x times 1 over x is just what? 1. So that would be our derivative. Okay, not too bad, right? Number 4. Here's the mistake people make with number 4. They say, oh, if I want to change the name of this, I can just bring that 3 out in front. You can't do that. The only way you could bring the 3 out in front is if you had the natural log of x cubed like this, where it means that. Now you'd be allowed to bring that 3 out in front, okay? But not in this case. We have to think of this as, here's our u. This is u cubed. That's the way we have to think of it at the beginning. This requires the chain rule. What's the derivative of u cubed? 3u squared, okay? Times the derivative of the u. Well, what's the derivative of the u? What's the derivative of ln of x? 1 over x. So now combining these, we're just going to have 3 natural log x squared all over x. That would be the derivative there. Can I bring this 2 down in front to simplify it? No, because it's the natural log of x, that whole thing squared, not just the x getting squared. If it were just the x getting squared, I could bring it down in front. All right, so now let's look at some cases where it is good to expand. Look at number 5. I would like to rewrite this so that the problem is easier. The way it is now, I would have to do 1 over my u, which would be this, and then I'd have to do the derivative of that. It's really difficult to do. But if I rewrite this as the natural log of x squared minus 1 to what power, am I allowed to bring that 1/2 out in front? Yes. So I can make this problem much easier by doing this. I have not taken a derivative. I've just rewritten the problem in another form that's equivalent. Now the derivative is pretty easy because I can do this. I just have 1/2 times something, so I can just bring down the 1/2. Times, what's the derivative of natural log of u? 1 over u. Times, what's the derivative of the u? 2x. Now I can just multiply. What's half of 2x? X over x squared minus 1. That would be our derivative. Okay? Don't write this down, but let me just show you how this would have had to been done if I didn't know to expand first. I'm going to go from right here. Just watch. If I went from right here and took the derivative is going to be the derivative of natural log of u is 1 over u. Then I'd have to do times the derivative of the u. Well, I have to think of this as u to the 1/2 to take that derivative. And then I have to keep going. And I have to say, what's the derivative of the inside? So now I have to simplify all of this. Well, this isn't too bad. Half of 2x, I already know that. But now I'd have an x on the top, and then I have this to the 1/2, and this is to the negative 1/2, so it would have to go to the bottom. So what do I do if I bring this to the bottom? What would I do with the x squared minus 1 then? Add them, right? Because I'm going to have this to the 1/2 plus this to the 1/2. So what's it going to be then? Just to the first. See how I get the same answer, but wasn't that a lot more difficult? I think some of you weren't really following even on that because it is a tough way to do it. Now, this problem, this one looks like it would be impossible to do. And it would, unless you know how to expand first. If you know how to expand this, the problem is actually pretty easy. Okay, so let's think of what we can do. Well, I'm going to write the natural log of x. This is multiplication. What does multiplication turn into? Addition. So plus natural log of x squared plus 1 squared. What does division turn into? So I have minus the natural log of 4x cubed minus 1 to the 1/2. Having it written like this is better, but it would still be difficult. Because when I get here, I'd have to do 1 over this times the derivative of this and would use the chain rule. But what am I allowed to do with that 2 at this point? Bring it in front. I still have not taken the derivative. So this is going to be this now. Now I have something that's pretty easy to differentiate. I'm taking the derivative, so I'm not going to write this anymore because now I'm actually doing the derivative. Derivative of ln of x is 1 over x. Plus, I'm taking the derivative here. I just bring down the 2. The derivative of ln of something is 1 over that something times, what's the derivative of that? Good. So there's my next term. My last term, I bring the 1/2. The derivative of ln of something is 1 over that something. And then times, and then what's the derivative of this? Right. Okay, so now we have to simplify this. What you want to look at is that terms are separated by pluses and minuses. So this is going to be one term. That one doesn't need to change. This is going to be my next term, all of this together. And this is going to be my last term. And I need to simplify each of them if I can. Nothing to do there. This one, I have 2 times 2x. Well, that's 4x. So I'm done with that one. This one is minus. I have half of 12x squared. What's half of 12x squared? So I'm going to have 6x squared. I took care of that and that, all over 4x cubed minus 1. This should be the answer in the back of the book, or the answers on Canvas. But if you look and it's something different, what might they have done if it's something different? Gotten a common denominator. So if you see a real ugly answer in the back or on the Canvas solutions, that's what they may have done. So I'm not going to make you get a common denominator on things like that. All right, any questions? So what's the derivative of natural log of x? 1 over x, yes. It's on your green sheet too, on the derivative side. I think it's number 14 maybe, something like that. All right.